And now we come to a very, very important point. Proving that things are not regular. So let's consider this language here, the language of strings 0 to the n, 1 to the n, when n is bigger than 0 or 0. So this would be the sets of strings epsilon, the empty string, or 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. So the same number of zeros as ones, and all the zeros come before the ones. Is this language regular? Now, if you think about it, it seems like it's not, because the DFA will need to remember how many zeros it has read to match it with the ones. But DFAs only have a constant amount of memory, so you can't really remember that. But can you prove it? Well, there is a tool, a very important tool, to prove that something is not regular. And it's called the pumping lemma. And the pumping lemma says that if L is a regular language, then blah happens, okay? Some mess of quantifier and symbols. So let's see what this mess says, okay? If L is regular, then there has to be some p, possibly 0, some integer p, okay, such that all the strings in the language L which have length at least p can be decomposed, can be written as x, y, and z, okay, where the y part is not 0 and the xy part has length at most p, such that for every I, if you pump the y by repeating it, obtaining the string x, y to the I, z, then this new string will still be in L. Okay? Recall that y0 is epsilon, y1 is just y, y squared would be yy, y cubed is yy, and so on. Okay, so in other words, we say that if you have a regular language, then sufficiently long string, any sufficiently long string can be written as xyz, and then if you repeat the y as many times as you like, the new string will still be in L. Okay. That's the content of the pumping lemma. So what's the proof idea of this? Okay. So if you have a DFA that recognizes L, okay, let me choose P to be the number of states in Q. The number of states Q. Okay. Now let's consider a string whose length is at least P. Okay. Let's consider the trace of M on W. Okay. Remember that the trace of M on W has length P plus 1. Okay. And because you only have P states, okay, when you do the computation, some state has to repeat. Okay? So two states must be the same state Q. So Y now can be taken to be the portion of the string that brings Q back to Q. This would be Y here. Brings Q back to Q. And now it should be clear that you can repeat or even remove y if you choose I equals to 0, and the DFA will still accept the string. This is just an idea to show you where these y, I, and p come from. So the pumping lemma is not useful to prove that something is regular. It's useful to prove that something is not regular. To show that, we're going to use the contrapositive. If L is regular language implies A is this thing here in the box, is the same thing as saying that not A implies that L is not regular. Okay? So if you can prove the opposite of the box for your language, then the pumping lemma implies that this language is not regular. Okay? So we're gonna show the contrapositive of the stuff in the box. Okay? And this is the formulation. Here is the contrapositive. How do you get the contrapositive? You flip for all into exist and exist into for all, and you complement the final statement. Okay? So the complement of A would be that for every P, you can find a string of length at least P, such that for any decomposition, you can find an I where x, y to the iz is not in L. If you can do this, then L is not regular. So to prove that L is not regular, it is enough to prove not A. Not A is the stuff in the box. You have to prove the stuff in the box, and then L is not regular by the pumping lemma. So proving the stuff in the box means proving something like for every blah there exists blah, for every blah there exists blah blah, and so on. And this is winning a game. You should think of this as a game. You're playing a game, you want to win the game. And theory is all about winning games. Let's do an example. Let's consider the game Name the Biggest Number. There's two players, you and the adversary, and the rules. First, the adversary says a number, okay? And then you say a number, and you win if your number is bigger. Can you win this game? Of course you can. You have a winning strategy, okay? It's a trivial strategy. If the adversary says x, you're going to say x plus 1. What is x? What is x? I don't know. X is whatever the adversary does, okay? Is the adversary move, okay? It's whatever they do. Could be 5, could be 15, is whatever the adversary does. You can do x plus 1 and win this game. So you and the adversary exist and for all, okay? And the rules are a statement like the A and not A in the pumping lemma, okay? Specifically, the rule is that for every x, there exists a y, such that y is bigger than x. And having a winning strategy is saying that this claim is true. This claim here is true because for every x, for every move of the adversary, you have a move, exists y, such that y is bigger than x. Because you have a winning strategy, the claim is true. Let's do another example. The theorem that for every NFA, there exists a DFA that computes the same language. We already saw a winning strategy for this game. What is it? It's the power set construction. Okay? The power set construction is the winning strategy. If the for all player gives an NFA, the exist player can exhibit a DFA with the power set construction and win this game. And there's games with more moves, like chess, checkers, tic-tac-toe. There are games with more moves. And you can win if for every move of the adversary, there exists a move that you can make, such that for every move of the adversary, there exists a move that you can make, such that you eventually checkmate in chess or something else, in tic-tac-toe. So the pumping lemma is a game. Okay, it may not be as fun as chess, but it's a game. It's an interesting game. And again, I'm working with the contrapositive, which is what you need to prove that L is not regular. So what are the rules of the game? The adversary is for all. So the adversary is going to pick P. You do not have control on P. Okay, you don't get to pick P. Okay, in chess, if you play black, the adversary goes first and plays a move in white. You don't have control on the move, okay? For every move, you have to do something. So here, for every p, you have to do something, okay? You don't get to pick p, okay? The adversary picks p. Now it's your turn. Now you get to pick w in L of length at least p. Okay, you have to pick w in L of length at least p, but you can pick any w that you want with these constraints. Now the adversary makes the decomposition w in x, y, z, where the length of y is bigger than 0 and the length of x, y is at most p. And finally, you get to pick I, at least 0 or bigger than 0. And you win finally if the final string x, y to the I, z is not in L. That's when you win. Okay? So is this game? Your moves are these. The other moves you don't get to control. Let's see an example. Let's do the theorem that the language 0 to the n, 1 to the n is not regular. Here is the stuff in the box for the contrapositive. This is the game. This is the game that we're playing. Okay, so let's see. We're going to use the pumping lemma. The adversary moves p. What is p? I don't know. It's some number p. I have to win for every p. That's when I move. That's when I win. Okay, the adversary moves p, so I'm going to pick a string, and the string that I pick is this. Is 0 to the p, 1 to the p. Okay, so for every move p of the adversary, I'm going to pick this string here. So my string is defined in terms of the move of the adversary. Okay? This is necessary because my string has to be of length at least p. So my string always has to depend from the move of the adversary in some way, at least in terms of length. Now the adversary moves x, y, z, okay, some decomposition, and I'm gonna move now I equals to 2. So how did I pick I equals to 2? How did I pick this w? This is with the hindsight, you know, after you do these things several times, you get a sense of what are good moves. Just like when you play chess, it takes you a long time to get a sense of what are the good moves in chess. So to win, we have to show that the pumped string, which is now x, y, y, z, is not in L. Okay, and here is now how we can show that. Well, the length of x, y is at most p, and the original string w, which is x, y, z, is 0 to the p, 1 to the p. Okay, what does that mean? It means that the y part only has zeros, right? Because x, y have length at most p, and you had p zeros at the beginning. So this pumped string x, y, y, z is of the form 0 to the p plus length of y. So you have p plus length of y zeros, and then 1p. But y was not empty. The length of y is not 0. So this thing is not of the form 0 to the n, 1 to the n. You have more zeros than 1. So you place the string outside of L and you're done. You won the game. This language is not regular. It's not easy. It takes a little bit of time, okay? But we're going to see many examples of this. So let's see another example. Let's consider the language where w has as many zeros as 1. Okay, but not, the zeros don't have all to come before the ones. Okay, I'm going to do a similar proof. I'm going to use the pumping lemma. The adversary moves p, and I'm going to move what? I'm going to move again 0 to the p, 1 to the p. The adversary moves x, y, z, and I'm going to move what? I'm going to move again y equals to 2. And I have to show that x, y, y, z is not in L. And again, y only has zeros like before. So x, y, y, z has more zeros than ones, not as many zeros as 1. This is exactly the same proof, and it works even for this language here, which is a bit less structured than the other one. Okay, let's now see a slightly different example. Let's do the language of 0 to the j, 1 to the k, where j is bigger than k. So you have a bunch of zeros followed by strictly less ones. I'm going to use the pumping lemma. The adversary moves p. I'm going to move what? What's my move here? I cannot do the same thing as before, because the thing from before had the same number of zeros and ones, and now you have to have more zeros than ones. So I'm going to move w, which is a 0 to the p plus 1, 1 to the p. Okay? The adversary moves x, y, z, so it picks a decomposition. What's your move for I now? Can you make I equals to 2, 2, 3, 4, like before? You cannot, right? If you pick I equals to 2, you would just increase the number of zeros, but this would still be valid for this language. Instead, you have to remove zeros. So I'm going to move I equals to 0. We have to show to win this game that xz is not in L. Okay? Like before, because xy has length at most p, and my original string started with the p plus 1 zeros, y only has zeros. So xz has a number of zeros, which is a p plus 1, which is how many you had at the beginning, minus the length of y. Since y is not empty, you're removing at least 1 0, and so this thing is not anymore of the form 0 to the j, 1 to the k for j bigger than k, and you're done. Let's do one more example. Let's say the language of strings UU, where U is any string. So the same string repeated twice. We're going to use the pumping lemma to show that this language is not regular. Let's say that the adversary moves P, and we have to make a move. So what do we move? Any thoughts? We are going to move 0 to the p 1, 0 to the p 1. Okay, a little bit more complicated. The adversary picks a decomposition, and I'm going to move I, what? I'm going to pick I equals to 2. Okay, we have to show that x, y, y, z is not in L. Okay, same reasoning as before, y only contains zeros. Okay, so when you pump y, you get a string of the type 0 to the p plus the length y, 1, 0 to the p, 1. And since y is not empty, the first half of the pump string x, y, y, z only has zeros. Okay? So x, y, y, z is not in L. So if you think of the string, it has a bunch of zeros followed by 1, then a bunch of zeros followed by 1. So what I've done here, by pumping, I have inserted some more zeros here. And if you think of the midpoint of the string, it has moved a little bit to the left, which means now all the ones are to the right of the midpoint, which means that the string is not of the form UU anymore. Another example, let's consider the language of ones whose number is a square. So 1 to the n square. We're going to use the pumping lemma. So the adversary moves p. So now there's no zeros, so we have to be a little bit more careful. The adversary moves p. We're going to move what? We're going to pick 1 to the p square. Okay? The adversary picks a decomposition, and we're going to have to move I, and we pick any thoughts for I? we're going to pick I equals to 2. Again, we have to show that x, y, y, z is not in L. Okay, so now it's all about the length of the string because you only have one symbol, 1. It's all about the length of the string. So remember that the length of xy is at most p. So the length of x, y, y, z, the pumped string, is at most what? Well, at the beginning you had length p square. Okay, you pumped y, which is a substring of xy. So the length of x, y, y, z is at most p square plus p. Okay, but this thing is strictly less than p plus 1 quantity square. Moreover, y was not empty, so the length of x, y, y, z is strictly more than p square. Okay, so the length of x, y, y, z cannot be what? Cannot be a square, right? Because it's strictly between two consecutive squares. But it was supposed to be the language of squares, okay? But we found a string which is not a square obtained by pumping, so this language cannot be regular. And we are now finished with regular languages, and next goal is to move to context-free languages.